Audio Jungle. Audio Jungle.
Chapter 2. Components in Fiber Optic System. 2.1 Understand the main components in the fiber optic communication system. Optical source. Optical transmitter converts electrical input signal into corresponding optical signal. The optical signal is then launched into the fiber. Optical source is the major component in an optical transmitter. Popularly used optical transmitters are light-emitting diode (LED) and semiconductor laser diodes (LD). The optical source is often considered to be the active component in an optical fiber communication system. Its fundamental function is to convert electrical energy in the form of a current into optical energy, light, in an efficient manner which allows the light output to be effectively launched or coupled into the optical fiber. To a large extent, these two sources fulfill the major requirements for an optical fiber emitter, which are outlined below. 1. A size and configuration compatible with launching light into an optical fiber. Ideally, the light output should be highly directional. 2. Must accurately track the electrical input signal to minimize distortion and noise. Ideally, the source should be linear. 3. Should emit light at wavelengths where the fiber has low losses and low dispersion and where the detectors are efficient. 4. Preferably capable of simple signal modulation, i.e., direct over a wide bandwidth extending from audio frequencies to beyond the gigahertz range. 5. Must couple sufficient optical power to overcome attenuation in the fiber plus additional connector losses and leave adequate power to drive the detector. 6. Should have a very narrow spectral bandwidth line width in order to minimize dispersion in the fiber. 7. Must be capable of maintaining a stable optical output which is largely unaffected by changes in ambient conditions, e.g., temperature. 8. It is essential that the source is comparatively cheap and highly reliable in order to compete with conventional transmission techniques. Transmission medium. A transmission medium is a physical path between the transmitter and the receiver. The fiber optic cable carries the optical signal from the optical transmitter to the optical receiver. Advantages of fiber optics for communications. There are a number of compelling reasons that lead to the widespread adoption of fiber optic cabling for telecommunications applications. Much lower levels of signal attenuation. Fiber optic cabling provides a much higher bandwidth, allowing more data to be delivered. Fiber optic cables are much lighter than the coaxial cables that might otherwise be used. Fiber optics do not suffer from stray interference pickup that occurs with coaxial cabling. Optical receiver. The first element of the receiver is a photodetector. The photodetector senses the light signal falling on it and converts the variation of the optical power to a correspondingly varying electric current. An optical receiver consists of a photodetector and electronics for amplifying and processing the signal. An optical receiver converts the optical signal received at the output end of the optical fiber back into the original electrical signal. Semiconductor-based photodiodes are the main devices that satisfy optical receiver requirements. The two basic types of devices used are called a pin photodiode and an avalanche photodiode (APD). The function of the optical receiver is to detect the incoming optical power and extract from it the signal, either analog or digital, that is being transmitted. Since the optical signal generally is weakened and distorted when it emerges from the end of the fiber, the photodetector must meet strict performance requirements. Among the most important of these are: 1. A high sensitivity to the emission wavelength range of the received light signal. 2. A minimum addition of noise to the signal. 3. A fast response speed to handle the desired data rate. In addition, the photodetector needs to 1. Be insensitive to temperature variations. 2. Be compatible with the physical dimensions of the fiber. 3. Have a reasonable cost compared to that of other system components. 4. Have a long operating lifetime. 2.2 Investigate optical sources in fiber optic communication system. Light-emitting diodes (LED). An LED is a junction diode made from semiconductor compound gallium arsenide phosphide. LEDs used as optical fiber transmitters emit infrared radiation at a wavelength of about 850 nanometers (0.85 micrometers). A light-emitting diode (LED) is a two-lead semiconductor light source that converts an electrical current into light. It is a PN junction diode, which emits light when activated. When a suitable voltage is applied to the leads. A light-emitting diode (LED) is known to be one of the best optoelectronic devices out of the lot. LEDs are very cheap and convenient source of light. LEDs are usually used with multimode fibers due to their low output intensity. LEDs are employed in low data rate digital transmission systems up to speed of about 30 megabits per second, wherein spreading of output pulses because of dispersion is not a big problem. A light-emitting diode (LED) is a semiconductor device using a PN junction diode that emits incoherent light through spontaneous emission when a current is passed through it. Typically LEDs for the 850 nanometer region are fabricated using gallium-3 arsenide and algaris. LEDs for the 1300 nanometer and 1550 nanometer regions are fabricated using Ingaras P and INP. LED emits light by spontaneous emission. Light is emitted as a result of the recombination of electron and holes. LEDs are junction diode made from compounds of gallium, aluminum, arsenic, As and phosphorus Ps. Spontaneous emission. An LED is a form of PN junction diode that is operated with forward bias. Combination of electron and holes in depletion region generates photons of light. A forward bias is applied, current will flow. As the electrons from the N-type semiconductor flow into the P-type semiconductor, they combine with the holes, releasing energy in the form of light and passes through an opening or lens. LEDs can be visible spectrum or infrared. LEDs are of interest for fiber optics because they are small. They possess high radiance, i.e., they emit lots of light in a small area. The emitting area is small, comparable to the dimensions of optical fibers. They have a very long life, offering high reliability. They can be modulated, turned off and on at high speeds. Characteristic of light source LEDs. There are 5 major characteristics of LED. Peak wavelength, spectral width, emission pattern, power, speed. Peak wavelength, the wavelength at which the source emits the most power. It should be matched to the wavelengths that are transmitted with the least attenuation through optical fiber. The most common peak wavelength is 780, 850, and 1310 nanometers. Spectral width. Ideally, all the light emitted from an LED would be at the peak wavelength, but in practice the light is emitted in a range of wavelengths centered at the peak wavelength. This range is called the spectral width of the source. Emission pattern. The pattern of emitted light affects the amount of light that can be coupled into the optical fiber. The size of the emitting region should be similar to the diameter of the fiber core. Power. Usually achieved by coupling as much of a source's power into the fiber as possible. The key requirement is that the output power of the source be strong enough to provide sufficient power to the detector at the receiving end, considering fiber attenuation, coupling losses and other system constraints. In general, LEDs are less powerful than lasers. Speed. A source should turn on and off fast enough to meet the bandwidth limits of the system. The speed is given according to a source's rise or fall time, the time required to go from 10% to 90% of peak power. LEDs have slower rise and fall times than lasers. Linearity is another important characteristic. Linearity represents the degree to which the optical output is directly proportional to the electrical current input. Most light sources give little or no attention to linearity, making them usable only for digital applications. Analog applications require close attention to linearity. Non-linearity in LEDs causes harmonic distortion in the analog signal that is transmitted over an analog fiber optic link.